Hello, my name is Gerard van Belle, and I'm an astronomer at the Lowell Observatory. And I'm very happy today to be talking to you about advances in instrumentation here at the observatory. It's an interesting line of work that I have. I do research with the facilities that are at the observatory, but I also spend a lot of time working on trying to make them more capable and add new sort of techniques that are possible for the astronomers at Lowell. And so I'm going to show you a few things that we have going on at the observatory that are really out on a very interesting cutting edge of astronomy. And so it's going to be actually a bit of a treat. We're going to immediately go inside a telescope dome. We have a telescope up on Mars Hill called the Titan Monitor. This is a 20-inch plane wave telescope. This was supported by a NASA grant, and we actually are able to go into the dome from a remote location. I'm a few miles away from Mars Hill, but we can actually do everything remotely from the comfort of our home. And so here we are looking inside the dome right now, and this is actually a desktop that is on the computer up there, and I'm able to pull it up as my desktop here at home. And so we have a little control window here that shows what the sky is right now, and excuse me, and we actually have a couple of webcam views, and I've actually gone ahead and turned everything on. It's actually a little unfortunate looking out the window here. The weather is actually cloudy and even a bit rainy right now. Otherwise, we could actually look at a thing or two in the middle of the day. The telescope pointing is very good. And so one of the things that would be easy to look at would be something like Venus right here. This software interface from PlaneWave is very nice. You just basically point and shoot, and then you click on Go To, and you can actually see in our little webcam windows here, the telescope is immediately moving from its current location over to pointing at Venus. And if it was a little more clear, we could actually snap a picture of that. The dome would be open. This slit right here would have actually slid all the way back, and the entire roof can rotate. I've actually left the power off on that right now because I don't want it to accidentally open in the middle of a bit of rain. But it's very interesting to be able to do this in the nighttime, be able to just click on things, and the telescope is off and running. So here's everybody's favorite star, Betelgeuse. Where did that go? Right there. Let's go take a look at Betelgeuse. If we could open things up, and if it was nighttime, we would be able to see this star, which has actually just returned to its normal brightness after having a very interesting dimming phase of going down about to only a third of its normal brightness. We'll be doing actually some virtual star parties in the near future with this facility, where we're able to point to things and take pictures. Normally at nighttime, there'll be a whole nother screen down here in the right-hand corner that'll have the camera that is taking pictures. One of the things that's on the cutting edge of research here and is an advance is that not only can it be used manually like this, but we're actually trying to make this a fully robotic observatory. The name of the observatory, the Titan Monitor, comes from the fact that it has a primary intent, which is to basically stare at Titan whenever that moon of the planet Saturn is up in the sky. And we want to monitor its brightness. And whenever it happens to have a change in brightness, that potentially can trigger some observing programs on larger telescopes, including the Hubble telescope, where we want to actually look at this moon of Saturn and try and find out new things about it. So it's very neat to be able to do this from the comfort of my own home, of being able to move things around. It's amazing to be able to click on things, and you can actually see this telescope that's many miles away, moving and going to places on the sky and doing work for you. So we can see it slewing around here. The mount is a very interesting mount. The mount is made by PlaneWave, and we actually have one of their 20-inch telescopes on here. We actually have a second telescope off on the side. This is a 12.5-inch telescope, and we use that for very high-speed monitoring of things. A very useful thing that we do from the observatory is look at the brightnesses of stars and see how they might drop if an asteroid is passing in front of the star. And that helps us measure the sizes of asteroids without having and we'll see if, sorry about that, looks like my audio just dropped a little bit. And so we'll be moving on from the TIMO telescope to an instrument that is getting built for the 4.3 meter telescope, our Lowell Discovery Telescope. Let me switch to the screens here and get over to that. So this has been very enjoyable. We currently have an instrument on the back end of our telescope called DISY, the Differential Speckle Survey Instrument. And this is a camera that is right here in the red box. And this is sitting on the end of the 4.3 meter Lowell Discovery Telescope. And we are able to look at many, many stars with this. We're currently conducting a survey called the Pokemon Survey, which is something that lets us look at all the nearby low mass stars. These stars are interesting because they are potential hosts of planets that are habitable. They potentially would be harbors of life. And these potential habitable stars are very small, so it's easy to directly detect the planets nearby them. Now, a problem we have when we look at stars at very high resolution is that the atmosphere blurs things out. So we get what we call speckles. There's a bunch of spots that we get. It's a lot like looking at a quarter that's at the bottom of a swimming pool. And we can try and actually get around that by taking very high-speed movies that don't actually make the images come into focus, but they do freeze out the turbulence of the atmosphere. So when stars twinkle above us, if you were to do that at very high speed, say 30 or 60 frames per second, you can actually freeze out that. And that's what this looks like, is this dancing star image here on the right-hand side. This was provided to me by my colleague Nick Scott over at NASA Ames, so appreciate that from Nick. And one of the things that you can do, a nice series of images from Nick, is show ways to combine this movie. And so if you just basically add up the images, you really don't get anything. You get basically a smeared image. And a better way to do this is to do a mathematical analysis of each frame before you add things back up. So this is called a Fourier Analysis. It's basically looking at patterns in the noise and patterns in the light that we're getting from the telescope. And if you add it up, you get these interesting waves that are a conversion of the image, which, if you turn it back into an image, reveals the fact that you can have very, very well-resolved images with where you can see a star, and then you get to see potentially detect close-in companions that would otherwise be washed out by the atmosphere. So that's what this instrument DISY is currently doing, and we're trying to actually build an improvement on that called QUIZY, which is the next thing. And we've gone from modeling this particular instrument. I'm currently using a program called FreeCAD because it's free and I can use it at my home office without having to pay for a very expensive site license of some other software. And we've gone from modeling this to actually having some very interesting builds of this. So the models have gotten actually more sophisticated, and we've been able to align everything. What's very interesting about building parts right now, building optical systems right now, is that the individual parts, you can actually download copies of models from various manufacturers, and then you can basically build the thing before you've actually built it. And so we get to assemble this in a virtual reality sort of scenario. And this has been very nice because then you can take it from that to actual reality. And so this is what the new instrument looks like in the lab, and all of those pieces now have been showed to be able to be built in a virtual sense. We're actually assembling this for real. Let me show some pictures of that, where we've taken receipt of a new camera. This is called an electron multiplying CCD camera from Andor Instruments, and we've been plugging them into the spots in the camera. You can actually see the detector back here, this Andor detector, and the individual elements here. And this is what it looks like when we turn things on. We have 4 starlight channels that are coming through the system. And then we actually have a separate channel that lets us sample and detect the turbulence of the atmosphere. And so we are continuing to work on this. We are in the process of trying to get this moved out to the telescope. And now we are getting ready to put it on a test telescope, a 1 meter telescope, before we move it out to the 4.3 meter. And so we, unfortunately, we were about a day away from moving out to this 1 meter telescope before we really, out of the sake of prudence, locked everything down because of COVID-19. And so now we're in the process of basically waiting this out, and we'll get back to this and get this on the sky soon enough. Okay, so one moment here. And so with that, this advance in trying to get this next generation instrument on here, we will be able to look for stellar companions next to host stars where there are maybe pairs of stars that are working in concert with each other. And these things will be able to exploit the full resolving power. So give me one moment here and try and tweak a technical difficulty here. It looks like my screen has stopped sharing. So I'm going to stop that, and then I'm going to restart it. All right, I think that might have solved our difficulty here. So let me just look for that and make sure that that has come back up. Hello. And now I think we're reshared. Ah, wonderful. Thanks for bearing with me. I appreciate that. So right now, we are able to look forward to getting this instrument out on a telescope we have at the Anderson Mesa site, which is about 10 miles outside of town. As soon as we're able to get back to work, we're going to be basically taking sensible steps towards that sort of status, but we're looking forward to it when that does happen. So one third thing I wanted to show some slides on is while we're on lockdown, I've been busy with trying to do additional design work on getting some instruments built. And I've actually been working with a company where I can actually show a implementation of this kind of work in a space-based environment, which is very interesting. One of the things that I've worked on over the years is designing and building telescopes called interferometers. And so what that does is you basically can make a big telescope from smaller telescopes. And there have been ideas on how to build an interferometer like this in space. And so this is, for example, this is a concept that University of Arizona put together called OASES. And you can see small telescopes here that are on this very large truss structure that are working together in concert. And they basically synthesize a much larger telescope. But the challenge here is that you can actually see, from the scale astronaut here on the side, that this is still a pretty big structure. So we've been trying to crack that nut on how to make it small, at least when it goes up into space and then maybe becomes big. And so I've been working with Made in Space as a consultant for a concept that we've been trying to put together. And what this does is this actually flies in a very small package. And then once you get to orbit, these booms that hold the telescopes out on the tips of these booms get printed while you're in space. And so this sounds actually mildly sci-fi, but actually Made in Space has been working on this for some time. This is my colleague Max over at Made in Space, showing one of the printed booms that comes out of one of their test rigs. And importantly, this sort of thing actually has versions of it that is already flying in space. So Made in Space has printers on the space station that are printing things for the astronauts. This is very useful. If you happen to need a particular instrument, there's two ways to get it. If you need a particular tool, then the one thing you could do is try and manifest it on the next Soyuz launch, or hopefully an upcoming SpaceX launch, and then wait, and then maybe 6 months later, if it's fast, it'll get sent to space. Or you send the file up, and 6 hours later, you have the print done, and you have the tool that you need. So this is actually a very innovative way to do things. And so we're thinking about how the telescope can actually print itself. And so in working with them, we've been designing this and thinking about how this gets put together. There'll be booms that get printed. And then my contribution has been looking at this optical payload that then makes use of the light from the two telescopes. And so we've been working in concert trying to come up with something that isn't just a PowerPoint design like this, but again leverages some of this work I've been showing on how we can actually design something and be able to put it together just like we did with that speckle camera. And so we can basically see parts that are available commercially from manufacturers, and we can actually spec that out and look at how we're going to put that together so that we can build this instrument and make it a reality. And so that's one of the things I've been working on while I've been there. All right. And so that is kind of where I'm at right now with the sort of work that I'm up to. And I am ready to take some questions from people if there is some questions that may have come up from that. I will leave this with an image of our Optimist spacecraft right now. Okay, so I see a number of questions here. I have a question from Victoria Gurgis saying, I've heard about observatories using lasers to account for atmospheric interference. How does that differ from dizzy and quizzy? So this is very interesting. One of the things you can do is you want to try and get a sense for the turbulence that's happening above your telescope. And a laser can actually be a reference point. When you basically shoot it out, you get some light that's backscattered back. And that basically gives you an idea of what the nature of the turbulence is. You could actually do that with the dizzy and quizzy speckle cameras to give you a measurement of the atmospheric turbulence. We're actually, it's for us with the science that we're doing, it's actually sufficient just to use the object itself that we're looking at to provide a probe of the atmospheric turbulence for us. And so that's the reason why we showed that there was those two patterns that are coming out of our new speckle camera, that grid pattern and the 4 spots. The 4 spots is basically the science, and that grid pattern is basically the technical engineering data that's going to let us take the twinkle out of the stars after the fact when we analyze it. So I see another question here from Jay Gibson, 2002-1984. What's the expected improvement in resolution with the new instrument over the unit currently in use? So the unit that's currently in use actually already gives us the full diffraction limit of the telescope. Basically, as a telescope gets bigger and bigger and bigger, your ability to pick out fine detail on the sky improves. And if you can basically account for the atmosphere, which would normally blur things out, and get the full potential power of a big piece of glass that's your main optic in your telescope, then it's said to be diffraction limited. The new camera actually can't improve on that, so we won't get any additional resolution. What's very interesting about the new camera is rather than doing measurements in 2 colors simultaneously, we'll be doing 6 colors simultaneously, plus this wavefront channel. That's that grid I was talking about. And so our ability to take out the smearing of the atmosphere will improve quite a bit. And so we're looking forward to taking advantage of that new flood of data that will come out from this much more capable instrument. I have another question here. This is from my colleague, Phil Massey. This should be a hard question. When the issue of astrometry from space, quote unquote, was first mentioned at a lunch talk, I was a grad student. My thesis advisor was very puzzled, and he said, how are they going to get the plates back? This is actually maybe reflective of how the landscape of astronomy has changed over the years, which is when astronomy was first done back, when rocks were soft, when Phil was a grad student, the usual way to collect light and capture light inside of a telescope would be with a photographic plate. And so old cameras, kids used to use chemicals to take pictures, and nowadays your cell phone, for example, it has a digital detector. That's going to be this thing right here. And so it basically takes the light that is focused on it, and it converts it directly into electric signals, and that's how pictures get put back together. It is true, actually, though, that early satellites used real film. And so there's a whole art to getting those film canisters back from the early satellites. This is particularly true of spy satellites, where they would eject film canisters, and they would re-enter, and these film canisters would parachute down, and they would catch them with airplanes in mid-flight and capture them that way. So, all right, Tom Curry, are any of these technologies available for citizen scientists? So there is not a lot of work done on speckle, which is to say high-speed imaging with electronic cameras on telescopes by amateur astronomers, but that is increasingly becoming an option for those that want to try these things out. You can, the sort of detectors that let you take very high-speed movies of the turbulence of the sky at very high magnification. That is something that's actually increasingly possible for amateurs to try out. And I know that there's a number of software packages out there that are on some of the amateur communities that allow you to try to do some of this more advanced reconstruction of images to get at the full resolution of the telescope, even in the presence of turbulence. Okay, I have a question here from Haley Osborne saying, I don't know if you said this already, but what materials would be using to print these interferometers out in space? So there's a whole, one of the interesting challenges of working with the whole milieu of 3D printing right now is that the materials technology is moving so fast. The printer technology itself is moving fast, but the materials that go into printers is going very quickly. And so I know there's a whole cottage industry right now for coming up with new materials for 3D printers in general, but for space-based applications, people are working on space-rated materials as well. In the particular case of Optimist that we have right here, our baseline material is basically a plastic-like material. And there may be other things that we look at in the future as well, but this is something that we've shown to be something that's workable, and we're pretty happy with the sort of expected performance that we have out of this printing. Let's see. I have a question here from Ian McLennan saying, please elaborate 3D printing. What do you anticipate in terms of basic materials? That's what I was just talking about. Terry Pantano, is the space station's 3D printer laying down metal or plastic? I believe on the space station it's laying down plastic right now. Gene Hill has the same question, type of materials. And Stephanie Van Belle, my wife, has a question about the alloy they would use to 3D print the telescope room. So again, these are all a lot of interest in the kind of material here. Yeah, materials are an interesting area of research. Right now we have something that works and maybe something else in the future. All right. Jason C. asks, how accurate are the current telescopes at finding technosignatures in space? So an interesting element of looking for things in outer space is over the last 20 years, we've had a very exciting set of developments in astronomy where we've gotten very good at finding planets nearby host stars, which is very hard to do because it's a lot like trying to look for a firefly next to a spotlight that's pointing straight at you, then they're like 2 feet apart at a distance of 20 miles in the fog. And so it's very hard to kind of tease these things apart. And the question of not just finding planets is something that astronomers think about, but even finding evidence for intelligent life on these planets. So, for example, science fiction writers have hypothesized that a very advanced civilization would want to come up with ways to capture the most amount of light and generate the most amount of real estate for their civilization if it's being hosted by a particular star. And so we build something called a Dyson sphere, which goes completely around the star, captures all of its energy. At least in theory, you can build something with enough materials that you break Jupiter apart. It's probably hard to do. But the idea there is that if some civilization somewhere has done this, you should be able to see the signature, this techno-signature, in that the light of the star should be changed or getting blocked in and out if this structure is going in front of the star or not. And so if such a thing existed and we looked hard enough, maybe we could see it, but that's hard. There are other things that have been speculated on how we would technologically find a technologization around another star. We're having a hard enough time in astronomy right now looking for planets around stars and trying to find the smallest of those planets that could potentially be Earth-like, in Earth-like orbits, potentially harbors of liquid water. We think those are the places to look for evidence of life on those planets. But all of those steps are still many years away of trying to even come up with that kind of evidence. So this is something that is an interesting challenge, and one of the reasons why I'm very interested in working on instrumentation is because that allows us to really push the frontiers and try and get at these very exciting measurements. Let's see. John, I'm going to massacre this last name, I'm sorry. Scarangelo, I hope that was close, saying, what would we look at with Optimist? Well, I'm glad you asked that. Optimist, this model we're working on right now, would have a effective size of about 20 meters in size. And so it would be able to have the resolving power of a telescope as if it were 20 meters in size. Currently, the largest operational telescope in space, the Hubble Space Telescope, is 2.3 meters in size. And so this physically is 10 times larger. You get 10 times finer detail on the sky. And so we could look at actually all kinds of interesting things. We could actually much more finely detail from this distance, from Earth, surface features on Pluto. We could look at the details of stars that have gas rings around them and dust rings around them, the youngest stars that are out there that potentially have planets forming out of that gas and dust. And we could look at actually trying to characterize the processes on how the clumps in the gas and dust around those baby stars collapse down into becoming planets. We don't really have a good handle in astronomy right now on exactly how planets come to be around the stars that host them. We've found that over the last 10 years, we've established that the general tendency of stars is to have planets, but we're still trying to connect the dots on how all that happens. From Umbriaco, what is the magnitude limit on Optimist targets? Right now, we're trying to come up with a baseline instrument that would get down to about 12th magnitude, which beats anything on the ground by a couple of magnitudes. There are permutations on this design which go even deeper. One of the things we're looking at and thinking about is ways to apply this to looking at asteroids in our solar system. This could let us map the asteroids without having to send a spacecraft there to do the individual mapping. We would have so much spatial resolution, we could actually pick out fine details from a great distance, from a spacecraft that was orbiting in the vicinity of the Earth, and being able to see 100 million miles away or something like that. And so these are the reasons why you would look at building a vehicle like this, a spacecraft like this, is you get extreme resolution, and it lets you do pretty amazing things in terms of seeing details at a very great distance. And with that, I think I have actually gone through most of the questions. Is there, with that, I will maybe check back in with my host, Jeff Hall here, and we can see what's going on, or we can actually sign off. And I want to thank everybody for checking in with the observatory right now. We've all been sequestered at home, and so it's not nearly as good as coming to the observatory and meeting people in person, but it's neat to be able to host everybody and see everybody here and get a chance to talk about the sort of work that really excites me and I think is out there on the cutting edge and is going to lead to amazing new discoveries and give us new windows and new insights onto this wonderful universe around us. So thank you for coming, and I will hopefully see you guys virtually in the